Hi class, welcome back. Today we're going to talk about 2.6 related rates. In this section, our goal is to be able to find related rate type of problems, be able to translate a real-life phenomena into mathematics, use related rates to solve these real-life problems. So we'll begin by describing the approach that we want to take when we're solving these type of problems. I know that sometimes word problems are overwhelming, but our goal is to be able to break it down into a consistent approach that we can feel comfortable replicating later on our own time. So my suggestion is to obviously read the problem. Sometimes it requires to read the problem twice, 3 times, 4 times. And then usually at the last part of the problem, it kind of gives you a question. It tells you the question of the problem. So identify what are the unknowns of the problem and what's given to you. And then from there, the next part is to find an equation that relates the unknowns with what's given to you. And then create an equation, make a picture, and then use derivatives to be able to find the related rate of the problem, and then using calculus you can find the solution for that and then be able to interpret the problem. So a lot of these problems have to do with chain rule and implicit differentiation, so it's important for us to master those skills from the previous sections to be able to move on to this section. A lot of the problems that we're going to be using relates to time, so a lot of the problems will be depending on time, and that's sort of the normal in these type of problems. So when we're dealing with related rates, we'll try to figure out the main equation that relates all the unknowns. So in this example, we have water that is drained out of a conical tank. Conical means a cone that is 3-dimensional. The volume of V with volume V and radius R. The height h of the water level are all functions of time t. Knowing that these variables are related by the equation given here, so we can see the relationship between them. Usually this is what you have to find. You can differentiate implicitly with respect to t to obtain the related rate equation. From this equation you can see here that if I take the derivative in respect to time on both sides of the equation and then treating r and h as the unknowns, as the variables, we'll be able to find the derivatives in respect to time. So derivative in respect to time is dv dt, since we don't know what v is. Pi is a constant, r is a variable, h is a variable, so we'll be able to find these unknowns. So v is related to the rates of change of both h and r. Now a lot of times we try to give this only to leave it in one single unknown variable. Instead of having both h and r being unknown, we try to find a way to relate h into r or r into h. That's actually a lot of times the key in order for us to be able to solve these problems. So let's look at example 1. Two rates that are related. Suppose x and y are both differentiable functions of t. That means they both depend on t, and are related by the equation y equals x squared plus 3. Even though y depends on x, it is assumed here that both y and x depend on t. They're asking us to find dy dt when x equals 1, given that dx dt is 2, and when x equals 1. So they're asking us to, in this example, this is more direct because they are telling us what to find, right? We don't have to interpret the problem. They're asking us what to find. They already gave us the equation that we need to use. They're giving us the constraints of the problem, right? So they're giving us this. They're giving us this is what we need to find, and they give us the relationship. So given that dx dt equals 2 when x equals 1, let's find dy dt. If you guys notice, what I did here is I summarized the problem, right? I summarized what was given, and the equation that they gave me was y equals x squared plus 3. So this is the relation between y and x. So this is true every time for x and y. So what I'm going to do here is I'm going to find dy dt by taking the derivative of this equation, by taking the derivative of this equation in respect to t. So derivative of y in respect to t, do on both sides of the equation, so that sort of requires implicit differentiation. Dy dt is dy dt. The derivative of this will require for us to do one term at a time. The derivative of x squared in respect to t, in this case, because the independent variable is t, then x must be treated as a function. Do you guys see that? Notice that t in this case is the independent variable, so therefore x must be treated as a function of t. And also we said it over here, x and y both are differential functions of t. So treat x as a function. So when you take the derivative of this, you have to think about x as its own function that we don't know how it looks like, right? It's a function that is defined in terms of t. Anyways, so when you do the derivative of this, you're going to have to use chain rule. You have the inside function and you have a power that represents the outside function. So you have to use the general power rule. So bring down the 2, multiply by x, and multiply by the derivative of the inside function, in this case dx dt. Plus the derivative of a constant. The derivative of constant is always 0. So therefore we have this equation. Now in this equation, we already know what x is. It's equal to 1, and we know that dx dt is equal to 2. So we're going to go ahead and replace those. So we have 2 times 1 times 2 equals 4. And there you go. We found the derivative of y in respect to t. So if you guys notice, our goal is to be able to find the equation of relationship between the two unknowns, or 3 unknowns, or 4 unknowns. Summarize what you're given in terms of rate, and then recognize what you're asked to find. If it helps if you actually create a picture of it, sometimes that's actually more, very helpful. So we'll try a few more here. So we have a pebble that is dropped in a calm pond, causing ripples in from concentric circles. The radius r of the outer ripple is increasing at a rate of 1 foot per second when the radius is 4 feet. At what rate is the total area A of the disturbed water changing? So if you guys notice here, a few things are established, right? The last sentence tells you what you're looking for. The word what is asking you a question. What's the question? What is the rate of the total area of disturbed water changing? How do we interpret the word rate in mathematics? And in our course, we interpret it as derivative. So you're looking for the rate of change of the area, total area. So it seems like what we're going to do is you're finding the rate of A. In other words, the derivative of A, the derivative of the area. So how are you going to start this problem? Well, can we begin by finding the actual formula of the area? Because once you know the area, the formula of the area, you can just take the derivative. So you guys see how this is the motivation right now? So we're going to have to find what the dy dt is. So we need to find a relation between A and the unknowns. What were the unknowns? Well, the unknown in here is the radius, because if you're talking about radius of a circle, then you have that the radius is changing. So, and also if you guys notice, they kind of give you that hint over here. The radius of the outer ripple is increasing, meaning it's changing at a rate. What does the rate mean? Derivative of 1 foot per second. If you guys notice, also the word foot per second gives you a hint for rate. So what they gave me was that the derivative, the rate of the radius over time, right? Radius over time is 1 foot per second. So you guys see how we're given this? You see how we're looking for this? And we also know that we're looking for this in a particular time, at a particular moment. And the moment is when the radius is 4 feet, right? They say that in here. So it's sort of, we have a motivation that because we're dealing with a circle, and we're dealing with radius, that we define the area of the circle, right? And we obviously know that's going to be in terms of the radius, pi r squared. We can take the derivative of this in respect to time, right? Per second. Per second means that you're doing this in respect to time. So do the derivative of a in respect to time. Do the derivative of the right side in respect to time. So we're going to have to use implicit differentiation, right? dA dt equals the derivative of this. Well, pi is a constant. R squared is a function, right? Now r is a function of t as well. R is a function of t, so we're going to have to treat r as a function. And thus we're going to have to use chain rule. So use chain rule for this. So how do you do that? Multiply 2 by pi times r, right? The inside, subtract 1 and then multiply by the derivative of the inside. So this is what we did. 2 pi times r times the derivative of the inside in respect to time. We already know what r is, that's 4 feet. We already know what dr dt, that's 1. So we multiply everything and that gives us 8 pi feet per second. And there you go, we found the rate of change of the area over time. So here we have some guidelines that we want to follow. Again, as we mentioned before, identify all given quantities and the quantities to be determined. Usually the last sentence of the problem gives you that hint. Make a sketch and label the quantities. Most important part, write an equation involving the variables whose rates of change is either given or are to be determined. So try to put an equation that relates all the unknowns that are given and you need to find. And then use the chain rule, implicit differentiation, or both, so that you can find the equation with respect to time. After completing step 3, substitute into the resulting equation all the unknown values given in the problem, and then solve for any rate of change given. Then solve for the required rate of change. Now, word problems, it's important for us to sort of create a library of memory, right? One of the most hardest part is to write this equation, right? Find this equation, find this connection, because if you're not remembering a geometric formula or a algebraic formula, then you're gonna have a hard time connecting the unknowns. So it's important for us to review these as many times as we can. So here is a few verbal statements that we want to keep in mind when we're dealing with these type of problems. Velocity of a car, right? Velocity means the rate of change. Traveling in 1 hour is 50 miles per hour. So x is the distance, right? X is defines the distance, and dx or dt represents the velocity. I'd like to for you guys to think about the word per. Gives you the hint that you're dividing, right? Miles over hour, which gives you a rate of change. If you guys notice, that's sort of going to be consistent in every problem. Water is being pumped into a swimming pool at a rate, that gives you the word rate there, 10 cubic meters per hour. So because we're dealing with cubic, that means is meters, that means is the volume, and so therefore we have the volume over changing over time, 10 meter cubics per hour, where V is the volume. A gear is revolving at a rate of 25 revolutions per minute. Again, rate of change, right? Because you have change over time change. So angle over the rate of change of an angle over time. Population of bacteria is increasing at a rate 2,000 per hour. So that gives you, again, a rate of change. Here is another problem. Inflation balloon. Air is being pumped into a spherical balloon at a rate, hint, right? We already have a derivative here, of 4.5 cubic feet per minute. Find the rate of change of that radius when the radius is 2 feet. So here I made a picture, right? Now the picture of a balloon, is a balloon 2-dimensional or 3-dimensional? I think you guys agree that it's going to be 3-dimensional. Now, for the simplicity of the problem, it's assumed that the balloon is going to be spherical, right? We know it's not true, but we're going to assume that this is spherical. So there's some basic assumptions that we make when we're doing these type of problems. So then when you're pumping air into the balloon, we are assuming, right, you're given a rate of 4.5 cubic feet. Well, that gives you volume, right? That gives you a hint that this is the volume, the rate of change of the volume per time, right, over time. They're asking you to find the rate of change of the radius of r. So I need to find the relation between volume of this and radius. So they gave me the rate of change of the volume, which was 4.5 feet cubic per minute. They gave me, they asked me to find the rate of change of the radius over time when the radius is specifically 2 feet. So therefore, I have to find the relation between these two, right? Well, the relation between V and R as an equation is the volume. The volume of the spherical is 4/3 pi r cubed, right? We have to remember this one from our geometry. And then now that I have the relationship, I'm going to find the derivative of them in respect to time. So that way I can kind of use this, right? And I can find what I need to find. Even though R is not solved, that's not a problem because we're dealing this with implicit differentiation, right? So we can take the derivative of the left with respect to time and take the derivative of the right with respect to time. R is a function of time, so this is going to be treated as a function. So this is a constant. So what do we do with this? 4 pi times the derivative of r cubed. What do we do with the 3? We multiply with the r, take away 1 from the power, and then multiply by the derivative of the inside, which in this case r is the inside. So that would be dr dt. Notice that we don't know what that is because that's what we're looking for. Then we're going to solve for this by dividing both sides by what we have here, right? So what sorry, my bad, I skip a step here. Let's plug those cancel each other out. We know what r is, that's 2, so we can plug it in, and then that gives us 16 pi. So we can divide both sides by 16 pi. That will cancel each other out, and so now we have 4 pi over 16 pi, which is equal to 0.09 feet per minute, and that gives us the rate of change of the radius. All right. So we have another problem here that we can use for an airplane. So I'll add this to a second video.